Welcome to today's tutorial on signal decomposition and denoising using multi-resolution analysis in MATLAB. I'm Shanti. I work as a senior online course developer at MathWorks, makers of MATLAB and Simulink. In this session, we'll begin with an engineering problem related to multi-resolution analysis. We'll discuss why MRA or multi-resolution analysis is required. Next, we'll see how to solve the engineering problem we have. As part of it, we'll get started with MATLAB Online, available for this NPTEL course. Followed by, we'll dive into an activity focused on signal decomposition and denoising using multi-resolution analysis. We'll end the tutorial by summarizing the key takeaways and a Q&A session. I would like to emphasize that today's tutorial focused on using MATLAB to decompose and denoise signals without going too deep into theory. So to start with, we have an engineering problem here. So the central question here is, in many engineering applications, signals contain important features as well as noise, both of which are distributed across a wide range of, say, time and frequency scales. So extracting meaningful information from such signals requires the ability to distinguish between fine details, broad trends, and noise components, as you can see in this figure. However, there are some challenges associated with this denoising and decomposition of the signal. First is, features and noise often overlap across multiple scales, making it difficult to separate it. And secondly, if we are using single scale filters or traditional filters like low pass filter or high pass filter, it may either result in the loss of valuable information or fail to adequately suppress noise. And thirdly, many signals or many real world signals are non-stationary in nature, meaning their characteristics change over time. So this makes it difficult to separate the signals and noise effectively. Finally, to tackle these issues, there is a need to analyze and process signals at multiple scales or resolution. So how do we address these challenges of denoising signals if the noise and signals are present in multiple scales or resolution? So solution for these challenges requires some advanced techniques, and one among it is multi-resolution analysis, which we'll explore in this session. The solution approach for solving the engineering problem we have today is broadly divided into several steps. First, we will load the signal, bringing in the raw data that needs to be analyzed or denoised. Next, we move on to signal decomposition, meaning breaking the signal down into its fundamental components for more detailed analysis. Then we perform a pre-energy analysis to assess the energy distribution within the signal before any modification or any processing. And after that, we apply thresholding. So here we apply a threshold value so that to filter out unwanted noise or irrelevant information by setting some specific cutoff values. Following the thresholding, after we remove the noise, we conduct a post-energy analysis. This is to evaluate how the energy profile has changed after filtering and to see how effective was our noise reduction. Finally, we reach the reconstruction stage where we reassemble the process signal, which is ready for further use or interpretation. So these are the steps which we'll be implementing in today's session in MATLAB. So as a first step to solve this engineering problem and to go through the series of solution steps, we will get started with MATLAB Online. All the registered learners to this NPTEL course, Mathematical Methods and Techniques in Signal Processing, have access to MATLAB online and have access to these set of products. So we'll see how to access MATLAB online provided for this course. For that, go to the main page of NPTEL course, Mathematical Methods and Techniques. And on the left, come down to the MATLAB section. So when you click on this MATLAB button, you can see two options here, MATLAB Access and MATLAB Training. Click on MATLAB Access, which will give you a series of steps as mentioned here on how to access MATLAB online for this course. So as a first step, if you don't have a MathWorks account, you can create it with the link provided in step 1. And if you already have an account, you can directly go to step 2 and click on Access MATLAB for your NPTEL course. So when you click on this Access MATLAB for your NPTEL course, you will be redirected to the Access MATLAB online page where you can click Access MATLAB online. So when you click on MATLAB online, it will take you to the MATLAB online window, and you can confirm that with the URL here, which should say matlab.mathworks.com. So I have opened here the live script, which will be using for demonstrating the signal decomposition and denoising using a multi-resolution analysis. First, I will modify or structure this window so that we have enough space in the editor window. So I'll minimize the file pane here. And this is a live script where you have all the details of the engineering problem we are trying to solve today and the solution and stepwise approach for solving the problem. And the table of contents here is linked to the specific section. So it's for easy navigation to that particular section. So you click on this particular, any specific heading, and it will take you to that section in the live script. So just to reiterate, our engineering problem is how to decompose and denoise the signal if the signal and noise is present in multiple scales or resolution, and how we can solve this using multi-resolution analysis. So as the first step is to load and visualize the signal. And here I have used earthquake seismograph data. The data is recorded at Tasmania University, and it is available with the MATLAB online. Let's load the signal which we are going to work today. So we will use the load function to load the signal. Load scope timetable.mat. And we'll just see what this data set looks like by calling out the variable name or table name. Let's run the section by clicking on Run Section command here. So we get a timetable which has two columns. The first column is time information, on what instances we collected the data. And the second column is the vertical acceleration data of the earthquake data set. So extract the time data and we'll extract the vertical acceleration data and save it to a variable. So we'll save the time variable, time data to a variable t. We will use dot indexing property. So scope timetable dot t. have extracted the time data. And next, we'll extract the vertical acceleration data, which is saved in a COBE column. So let's call the variable as COBE equals COBE timetable. We'll use the same dot indexing dot COBE. Now, let's plot the vertical acceleration against this time to visualize our earthquake data, which we are working on today. And let's analyze the pattern of the signal. So we'll use the plot function, plot the time information and the vertical acceleration data. So we are plotting the vertical acceleration against time. Have given the title and X label and Y label here. Let's run this section and see the results. So we have here a plot of COBE earthquake seismograph. And here we can see the vertical acceleration data is being plotted over time. And the signal contains both earthquake vibration, which is our relevant signal or important information about the earthquake data. And also we can see some noise here. So here we have some small rapid fluctuations superimposed on large movements. So we need to remove this noise so that we can extract informative information from the earthquake data. To do so, first we will decompose this earthquake data into different scales so that we can analyze the signal structure in different scales or different frequency bands. And the technique used here is multi-resolution analysis. There are different ways of doing MRA, and we will be using a wavelet transform method called maximal overlap discrete wavelet transform, or MODWT. So MODWT, what it does is it decomposes the signal into several levels without reducing its length. This ensures that the time alignment and important features are preserved even after decomposition. So when we apply MODWT decomposition, it decomposes the signals into two main levels, which has detail level and approximation level. We can set how many decomposition or how many detail levels we want for decomposition purpose, and each detail level isolates variations in specific frequency band. And the approximation level captures the overall trend or the core structure of the signal. So since we are using a wavelet transform technique for multi-resolution analysis, we need to specify what or which wavelet we are using. There are different wavelets which we can use. For today's analysis, I'll be using SIM4 wavelet. The reason is it offers near symmetry and good time frequency localization, which is more suited if our signal has smooth trends and it will preserve the sharp features in the signals. And we can also decide on what is the number of decomposition levels we want to decompose our signals. So typically the number of levels is chosen based on the length of the signal, and the common approach is to select the number of levels using the formula, which is the level should be less than or equal to log of n. So where n is the length of the signal. So I have taken here the number of levels as 4 and the wavelet type or wavelet as SIM4. Now let's define the number of decomposition levels and specify the wavelet name, and let's decompose the signals using the MODWT function. So we'll say number of levels equals 4, and we will specify the wavelet name as SIM4. So once we set the number of decomposition levels and wavelet name, next is to compute the decomposition coefficients or MODWT or wavelet transform coefficients using the function. So let's save this coefficients in a variable WT, and the function we will be using is MODWT. And there are three inputs. First input is the signal where we want to decompose. And the second is our wavelet name, which is saved in W name. And the third input is number of levels. So here we compute the MODWT coefficients using the function MODWT. And after we compute the coefficients, we are visualizing the coefficients at each level. So the code is already written here for visualizing the coefficients. The code lines is simple. We have used only basic plotting functions, plot of WTI, where I is the number of levels. Let's run this section and see the results. So here we have in the results section, we have visualized the coefficients. As I mentioned, the level number of levels was set to 4. That means we have 4 detailed coefficient levels and 1 approximation level. So approximation level, as I mentioned, it represents the overall trend in the signal, and the detailed coefficients capture successively lower frequency details. Now, we will analyze the energy distribution for each of these levels before denoising. So this is to identify which component of the decomposed signal contain meaningful information and which level contains noise. So for this purpose, we analyze the energy distributions for each level. Next task is to calculate the percentage of total signal energy present in each detail and approximation level using the MODWT coefficients. So let's calculate the energy level, energy distribution for each level as percentage. So here we are using the formula for energy distribution, which is simply the sum of coefficients, squared coefficients, wavelet coefficients for each level divided by total summation of the squared wavelet coefficients. And for visualization purpose, we will use a bar graph to visualize the energy distribution. So we will use the bar function. We need to visualize for all the number of levels. And the value is saved in energy by level. Let's run the section. So here we see that there are a D1 to D4 detailed coefficients, and the energy distribution for each level is mentioned here or visualized here. And A4 is the approximation level. So if you interpret this energy distribution by level, high detail levels, that is D1 and D2, which has low energy at these levels, suggest that they primarily capture noise rather than meaningful signal content. So basically, D1 and D2 levels has more noise component than signals. And the approximation level, A4, this level typically contains the majority of the signal's energy, indicating it holds the main structural features of the original data. So now that we have visualized the energy distribution by level, the next step is to define the threshold and apply threshold for coefficient compression. So for applying the threshold or setting up the threshold, first we need to find the threshold value. So there are multiple ways of calculating the threshold. Here we are using a universal threshold estimation method. So here the threshold is estimated using median absolute deviation or MAD. And this is considered because it's a statistical measure that is less sensitive to outliers, making it suitable for noisy data. So we have the formula for calculating the universal threshold, which is threshold equals sigma, where sigma is the noise standard deviation, and a square root of 2 log n, where n is the number of coefficients at that level. So let's initialize the compression threshold for wavelet coefficients. So how many thresholds we need? We need those many threshold placeholders or compression threshold as number of levels. So we have number of levels set to 4, which indicates we have 4 detailed coefficients level, and we have one approximation level also, right? So we will set or we will initialize the compression threshold to a size of number of levels plus 1. So basically it will be 5 compression threshold of placeholders. And now we will calculate the compression threshold for each level of the wavelet transform. So for that, we need to have a for loop here. So for I equals 1 is to number of levels. So why we have set the for loop to only number of levels? Because for the approximation level, we don't need to calculate the threshold value, because the approximation level is where maximum signal content or minimal noise is present, right? So approximation level, this threshold value is always set to 0. So because we usually do not threshold the approximation level. So that's why the for loop is running from I equals 1 is to number of levels. So based on the formula we have seen already, let's calculate the threshold for each level. First, we'll calculate the sigma value. Sigma equals median of absolute value of WT, where our wavelet coefficients are being saved. We are using a median approximation deviation method. So we will use the same equation. So we have defined the sigma value, and now we will calculate the compression thresholds. So we are calculating the compression threshold for each level so that it effectively calculates the threshold for noise removal. We are using a universal threshold method, and we have already set the threshold for approximation level to 0. Let's run the section and calculate the compression threshold. Now, since now we have set the threshold value for each section, now we will apply this threshold to our wavelet coefficients. So for that, we will first create a copy of copy of the wavelet coefficients for thresholding, so that our original wavelet coefficients is not affected. So we will save it to a new variable WC. And this is where we will be applying the threshold. Now, since we have same like how we set the threshold value or how we calculate the threshold value, here also we need to have a for loop so that we apply this threshold value to each level. So for that, let's take the absolute value of the threshold by using the function ABS and save the threshold value or absolute value of threshold for each level. And then we will extract the wavelet coefficient for the current level so that we can apply the threshold value. So let's save the particular wavelet coefficients to W for the current level. Now we'll apply the hard thresholding technique here to this wavelet coefficients. So the function for applying thresholding is W thresh, and we have 3 inputs here. The first input is the where you want to apply the thresholding, which is W, and we can set here whether we want to do hard thresholding or soft thresholding. I'm selecting here hard thresholding. So it's mentioned as H, and then the third input is W, the threshold value, THR. So we have applied the hard thresholding here, and then we will save or store the thresholded coefficients back to the WC variable. So WC IDX, that particular index value equals W. So here what we have done, we have iterated over each compression threshold, and we have applied the hard thresholding approach to the wavelet coefficients, and we have saved back into WC. Now let's visualize the thresholded coefficients at each level. So for visualizing the thresholded coefficients, the same set of code is used here, how we visualize the thresholded coefficients before applying the threshold. Let's run this section and see the results. So if you see or analyze the results over here, we can say that small coefficients are often which are associated with noise, which we already saw in the energy distribution diagram. Like D1 and D2 is where more noise was concentrated when compared to the signal component. So that is being set to 0, effectively removing noise from the signal. And the larger coefficients, which represents the actual signal features, are preserved, ensuring that the important information is retained. So if you see here in the visualization, D1 and D2 is being set to 0, and the higher levels, D3, D4, and approximation level is being returned or preserved, ensuring that the important information, important signal information is retained and not removed along with the noise. Now, after applying the threshold to the detailed coefficients, we can again verify the results by analyzing the energy distribution, how we did for the previously before applying the noising technique. So for that, we will use the same technique of calculating the energy distribution for each level and then create a bar graph to visualize energy distribution. Let's run this section as well to do a post energy analysis distribution. So here we see that when you compare with the pre-energy distribution diagram and post-energy distribution diagram, we can see that energy is decreased significantly in the detailed levels from D1 to D4. And you can see D1 and D2, the energy distribution is set to 0, reflecting the effective removal of noise. And the approximation level, if you compare the energy level here, it has been increased to 30. Earlier it was somewhere around 20. And this shows that the noise has been removed from the detail levels, and hence the main signal structure become more prominent and the energy of the signal is being increased here. Now let's reconstruct the denoised signal and see see how the signal looks after removing the noise. So after thresholding the wavelet coefficients, we reconstruct the denoise signal using inverse MODWT. So MODWT was the function we used for decomposition of signals. So we will apply an inverse MODWT function to reconstruct the denoise signal. So in this task, we will save the reconstructed signal in COP1, let's say compressed. Equals IMODWT, which is a function, inverse MODWT. And remember, we have saved the wavelet coefficients in WC after applying the threshold and the wavelet name in W name. Let's reconstruct the denoise signal and visualize the original and denoise signals together. So here, blue color signal is the original signal and the orange one represents the denoise signal. So here, if you analyze the visualization, after applying the thresholding, after MODWT thresholding, and after reconstruction, the denoise signal appear much smoother, with much of the high frequency noise reduced or eliminated. And important features of the original signals, such as sharp spikes or key events, remain preserved and clear. So this is how we do denoising and how we reconstruct the signal after denoising. So to evaluate the effectiveness of our denoising process, there are multiple ways of doing it. Either we can calculate the signal quality matrices like signal to noise ratio or RMS value. Or another way of evaluating the effectiveness of the denoising processes to compare the frequency spectrum of the signal before denoising and after denoising. So for that, we will calculate the fast Fourier transform and visualize the spectrum and evaluate the effectiveness of denoising process. So for that, first thing is to calculate the sampling frequency based on the time vector T, which we already have. And this line number 125 calculates the sampling frequency Fs by taking the difference between the first two time points in the vector T and converting it into seconds and then taking the reciprocal. So this gives the number of samples per second. And next we calculate the number of FFT points or FFT length. And we use the function next power 2, which finds the next power of 2 that is greater than or equal to the length of the signal. And this is useful for optimizing the FFT computation, as you all know that FFT algorithms perform better with lengths that are power of 2. And then we generate the frequency vector for plotting using the computed or calculated FFT length. Now we'll compute the FFT of the original and denoise signal and visualize the spectrum. So for that, we will use FFT function. And let's first calculate the FFT of the original signal. So it's saved in K original equals FFT of COB, comma, NFFT. And we will calculate in the same way the denoised spectrum as well using the function FFT. And the input is the compressed COB signal, compressed, and the second input is NFFT, which is number of FFT length. And let's visualize the spectrum and see the results. So if you analyze the frequency spectrum here, so here in the diagram, black line black spectrum indicates the original signal spectrum, and after denoising, the spectrum is represented in blue color. So to interpret this frequency spectrum before the denoising, that is spectrum of your original noisy signals, shows that both the signal of interest, which is our earthquake vibrations, and noise is spread across a wide range of frequencies, and there are a lot of frequency content in the high frequency area, which is basically the noise. And after denoising, the spectrum of the denoised signal is showing more spectrum or more content on the low frequency area, which indicates the signal, and the noise component, which is high frequency component, is being removed, and the signal is well preserved. So this is how you evaluate the denoising process or denoising technique or method you have used for removing or separating noise from the signal. And I have also included some additional resources here in this script where you can go to these links and learn more about the multi-resolution analysis. And we also have an app for doing multi-resolution analysis, which is Signal Multi-Resolution Analyzer. And you can see how to use this app in this documentation page. So to sum up what we have done in today's session, so our objective was to remove noise from a signal without losing the important features, given the noise and signal are spread across multiple scales. And these were our observation. We used multi-resolution analysis to remove noise, and in the multi-resolution analysis technique, we used MODWT technique, which is more related to the wavelet transform, discrete wavelet transform. And the key takeaways are we saw an effective noise separation using this MODWT decomposition. And MODWT decomposes the signal into multiple scales, which isolates noise and preserving meaningful content. And also, we used a selective denoising technique, meaning we used universal thresholding approach to remove noise from wavelet coefficients without distorting significant events. We calculated a threshold for each level separately, detail level and approximation level, and used that threshold for denoising the signal. And we also compare the energy distribution before and after thresholding to ensure noise reduction while retaining the signal's main structure. And we entered the solution by evaluating or verifying the effectiveness of our denoising method by doing a spectral analysis method. We can also do it using calculating the signal quality metrics like signal to noise ratio or root mean square error value. So here we come to the end of the session. You can refer more examples in our documentation pages on multi-resolution analysis, and you can try out the multi-resolution analysis app as well. Thank you. Thank you all.